Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back.
Yeah, so right now we are discussing about recovery and recrystallization. Recovery is the process which precedes the recrystallization. And in the previous class, we have talked about the mechanism of recovery. This basically occurs through the elimination or annihilation of dislocations. When the dislocations get arranged in some low energy configurations, the dislocation density is going to reduce, and the regions around this arrangement will be free of dislocations, right? So that's how the recovery occurs as you heat the material at some elevated temperature. And once the recovery process starts, as you continue or heat the material to higher temperature, then the recrystallization process starts. So this is when the restoration of the material will take place, and the straining which was given to the material during cold working, that will be relieved. Okay, and we have also learned that for recrystallization to occur, you need a minimum amount of deformation. This is because the driving force for the recrystallization process comes from this deformation itself, which is given, right? So you can say that the driving force for recrystallization is the stored strain energy. Or stored energy of cold work, both are same. This is what drives the recrystallization phenomenon, okay? And that is why you need a minimum amount of deformation or cold work for the recrystallization to initiate when you heat the material, okay, for its restoration. So this stored energy of cold work that you have in the material can be in fact demonstrated, because any energy, as you might know, can easily transfer to heat energy. Right? So this strain energy that you have, this can also be released as heat energy. And we do have instruments which can capture this heat energy as it is released. Okay. So with the help of such instruments, it is actually possible to show that, when you give certain amount of cold work to a material, the energy is stored in terms of the strain energy. One such instrument is DSC, or differential scanning calorimetry, which basically measures the heat flow, right? So from this, you get to know different kind of phenomena that can occur in a material when you heat it, right? So that phenomena can also be release of the strain energy. Okay. So when the strain energy is released, as I said, this will be released in the form of heat. And since this particular technique measures the heat flow, it will show you a peak corresponding to the temperature at which the strain energy will be released, right? Because that will increase the heat flow and it will be captured by the instrument. Okay. And another way of looking at it, in a physical term as to how exactly this strain energy comes out, and the way you can visualize it is through two samples. One will be used as the standard, which is an annealed sample, and another is the cold worked sample of the same material. So you take these two samples in an instrument in which you can actually measure the power which is required to heat these materials to a particular temperature. So you can actually see the difference of power which is required to heat the standard sample and the cold worked sample to a particular temperature. Okay. So if that can be measured, you can display this difference, and that will actually indicate that the strain energy is being released because the power required to heat the cold work sample to a particular temperature will be lower compared to what you need for the annealed sample, because as you start heating, the cold worked sample would release the strain energy. Okay. So that is how you can actually experimentally see this, and it can be displayed in a plot like this. So as I said, there will be a power difference. The power needed to heat these two material, one the standard annealed sample and the cold work sample, there will be difference in that. So that can be plotted against the temperature. As you continuously heat it. So this is not isothermal, this is anisothermal heating. So as you anisothermally anneal these two materials, and capture the power required to heat these two samples, you can generate a plot like this. Right, so this peak that you see over here, that is where you have the maximum amount of strain energy released, and that corresponds to recrystallization. That corresponds to occurrence of recrystallization. But you can see that the release has started even before the recrystallization process, right? Because at every other point below the peak, you have some power difference, right? So that means below the peak also the strain energy is being released. Okay. So that is the recovery stage. As I said before, recovery precedes the recrystallization process, and during recovery also a certain amount of the strain energy is released, and that is what you can see from this curve also, right? So the same thing can be shown by the DSC experiment what I was mentioning. So you might know that DSC captures the heat flow, and that can be plotted against the temperature. So any event or phenomena which will occur during the heating process would either release or absorb energy. Okay, and as a result of that, you would either get an exothermic peak or an endothermic peak in this plot between heat flow and temperature, right? So if heat is released, then it will be an exothermic peak, and for the endothermic peak, it is just vice versa. Okay. So if I just want to show it by a schematic here, it might look something like this. Right, so you can see at a lower temperature, let's say, this is around 100 degrees Celsius. And on this side, let's say here it is around 500 degrees Celsius. And close to the peak, it is around 400 degrees Celsius. So at the lower temperature, up to about 300 degree or so, you can see that there is a broad exothermic peak, right, at this portion over here. Okay. So this is indicative of release of energy or release of heat. As I said, the energy will be released in the form of heat. So here you see an exothermic peak first, which is a broader kind of peak, and later on you see this sharp peak, which corresponds to the occurrence of recrystallization. Okay. So that's what you see when you see these exothermic peaks that indicate the release of energy. And in this case, it is the strain energy which is being released. So during the recovery process at lower temperature, it is a broader peak because you could see that from here also it has just started releasing the strain energy. And then when the recrystallization process actually starts, you have a large amount of strain energy being released, and that is why you see a sharp exothermic peak when the recrystallization process initiates. Okay. So like that, as I said before, you can also visualize this experimentally with this kind of measurement techniques. So now we need to understand as to what exactly happens during the recrystallization process. Okay, so driving force we have understood, it is the stored energy or the stored strain energy which is given to the material by the cold working process. And now as you heat it, this is going to be released, and we have just now discussed it as to how that occurs and how you can visualize that experimentally. Now as that happens, we will have the restoration occurring, which basically means that you are going to generate strain-free grains from those strained grains which are present in the cold worked material. Okay, so there are different models which are proposed to explain this phenomena as to how exactly the strain-free grains form. So each of these models considers a particular mechanism through the first nucleus of the strain-free grain that will form. For example, one of the mechanisms says it is through polygonization. Because it is a recrystallization process, right? You have to form the new strain-free grains. So you need a nucleus first, which will be free of any strain, and then as that nucleus reaches a critical size, it is going to grow and consume the strained grains. And that is how the strain-free grains will form all over the crystal, all over the material, and it will be recrystallized, right? So one mechanism says that the nucleus forms through the polygonization process that we discussed in the previous class, right? So this is basically arrangement of dislocations in a low energy configuration in an array like this, which reduces the energy, because when the dislocations are arranged in this manner, energy per dislocation will be reduced, and as a result of that, the energy of the system will also reduce, right? So now the adjacent regions of this dislocation array, regions like this, will be free of strain, right? Will be free of dislocations. So this polygonized grain, that this polygonized region that you have created now, if this attains the critical size, when this becomes bigger than the critical size, then it can act as a nucleus for the strain-free grains. Okay, so this is one of the mechanisms of the nucleation of strain-free grains during the recrystallization phenomenon. Okay, but there are other mechanisms also. So let us talk about those and try and understand as to how it occurs. So right now, when the material is in cold worked state, you have these strained grains with high dislocation density. So across a boundary, if there is a difference in the dislocation density or in the strain energy, then the region which is of lower strain energy can actually bulge into the higher strain energy region, and a small bulge can form which will be free of strain, and that can act as the nucleus. Okay, so let's say you have this boundary between two grains A and B, grain A has low strain and B has high strain. So there is a gradient in the strain energy along this boundary. Okay. So it will try and reduce the energy. So therefore, this boundary can bulge into the high strained region in this manner. A small bulge like that can be created due to this strain energy gradient. So this region now, this shaded region is free of strain, right? And again, if this crosses the critical size, then this bulge that you have, this bulging that you have in this boundary, okay, this one, this can act as the nucleus for the strain-free grains, right? So this is another mechanism of nucleation during recrystallization. Okay. So this mechanism we can call by this name, nucleation by grain boundary bulging. This was proposed by these two persons. Now, during this recovery process, the dislocations can also arrange themselves in other kinds of low energy configuration apart from the arrays that we have seen for the polygonization process. And one such low energy configuration is a subgrain which can form due to dislocation rearrangement. Okay, and these subgrains can also act as the nucleus for the strain-free grains to form if the boundary between these subgrains can take a high angle configuration. Okay, if the misorientation across the subgrain boundaries increases and it becomes high angle, then it can also act as a nucleus. Okay, so this mechanism that we are going to talk about right now talks about subgrain coalescence by rotation. So the subgrains can merge or coalesce together to form the nucleus, but for the misorientation across them to decrease, the merger or the coalescence alone is not enough. It also needs to rotate to certain extent so that the misorientation between them can decrease. So that is where the need of the rotation. So a subgrain can rotate and align itself with the neighboring subgrain, and then as the misorientation between these two subgrains due to this rotation comes down, then these two subgrain can merge into one, because now there is no orientation difference between these two subgrains, these two adjacent subgrains. Right? For that to happen, one of the subgrains or the subgrains which are taking part in this coalescence process have to rotate. And as it is aligned, the boundary between them disappears because now there is no difference, there is no orientation difference between these two subgrains. So therefore, there will be no boundary between them. And as a result, these two will now become one bigger subgrain. Let's say in the beginning, these two subgrains were like this. With some difference across this boundary, some difference in the orientation. Okay, so there is some misorientation across that boundary. But now, if the subgrain can rotate, then these two subgrains can align themselves. So that along this boundary now there is no misorientation. So this boundary will disappear and these two subgrains will now coalesce into one. Okay. So that's how this whole process can occur with the help of this rotation. And now when this merged subgrain attains the critical size, it can act as the nucleus of a strain-free grain. Okay. So what I meant to say when I say that there is some orientation difference, so that is in terms of the atomic arrangement that you have. So if this be the arrangement in the first subgrain, in the other one it is little different across this boundary. Okay. Therefore, these two different arrangement, for them to align into one, you need some rotation, right? So when that happens, then in both of these subgrains, the atomic arrangement is going to be the same, and therefore there will be no boundary between them, so they can coalesce into one bigger subgrain. So these are some of the models which explain the different mechanisms of nucleation for the strain-free grains to form during the recrystallization process. And this particular mechanism was proposed by this person.
All right. With that, we come to the end of this lecture. But there is more to come on this particular topic. So I'll be back very soon. Thank you for watching.